Thanks, Julie. I'm Auto Switch. I'm an application engineer with Emerson for scroll compressors. I'm on the air conditioning side of our business unit. I've been doing this for 7 years now, and before this, I had an architecture engineering firm for 5 years designing HVAC systems for K through 12 schools. And then before that, I worked out in the field, installation and in the lab and such. Today, the overall agenda is kind of going to be high level, but I think it should be a good thing to, it'll be helpful to better understand where the compressor and different commercial systems. I'm going to try to stay away from the residential side of things and really focus on commercial and kind of high level, but at least show the applications and where they're used and what each type of system is and the various systems that are used in the commercial side of the field. I'm going to start with the refrigeration. We're going to go quickly on these. I think a lot of people will probably have experience on that. I'm going to keep it high level. As you can see, the compressors, the main part, it's kind of the heart of the system. It moves refrigerant. So, you know, the refrigerant's going to leave the compressor. It's going to be a high pressure, high temperature vapor leaving, go to the condenser. And you're going to have a condenser fan blow air across the condenser. So the fan's going to be cooler air blowing across the condenser, and it's going to try to cool down that hot refrigerant. So it's going to cool down that hot refrigerant, and the refrigerant's going to move to the metering device. That metering device can be an expansion valve, an orifice, valve, or electronic expansion valve. A lot of it's going to depend on the specific system type. So that's going to regulate how much refrigerant goes into the evaporator by controlling the superheat on the suction line going into the inlet of the compressor. So as the refrigerant moves through the evaporator, you're going to have a fan blowing across that evaporator, and that fan's what's going to be supplying that supplied air to the space. So when cooling, you may try to get 55-degree air supplied to the space. So you may have refrigerant coming into that evaporator at, 45 degrees, and it might leave that evaporator at 52 degrees. You may have the return air going into the evaporator at 75 degrees, and that evaporator is going to cool that down to 55 degrees. So then the refrigerant warms up, it's going to come back to the compressor, and it's going to keep doing over and over again to control that supply air temperature to condition the space. I'm going to quickly show heat pumps. Cooling mode in the heat pump's the same as what the cooling mode is in a strict AC only system. The only difference is there is a valve here. So in cooling, valve does the exact same thing. It goes to the outdoor condenser first, then it comes into the evaporator. Does the same thing that you would typically see in a straight AC unit. Heat pump, that reversing valve, instead of sending it to the outside condenser first, it brings out hot refrigerant to the indoor coil, what's typically called the evaporator coil, and that is used to heat up the air. So you might have 75-degree air returning back to that evaporator, and then as you blow that air across that hot coil, that's going to increase that air to 90, 95, 100 degrees to condition that space. Move into more of the commercial air movement systems. So I'm talking, we're conditioning air at this point. Later we'll talk about something that conditions water, chiller applications. Typical rooftop unit applications include VAV, variable air volume, CAVI, constant air volume, DOAS, dedicated outdoor air systems. There's other systems as well. These are just, the three most common type systems. Each of these systems will act differently also. The VAV system, all these systems will bring and have the potential to bring in some outside air as well. And it's not just going to be return air for all the spaces. And I'll go a little bit more in depth on each of these systems as we go. Here's an example of a typical rooftop unit. Just trying to show how the air moves. Some people may not be aware of what the actual VAV or constant air volume system does. I want to point out before I get started is that not every system's going to have this exhaust air. This exhaust air is good for properly pressurizing the building, but sometimes you may not need that in every space. So we're going to start with outside air. With typical buildings or rooftop units, going to bring in some outside air, and it's going to vary what that percentage is. It's going to depend on what your ASHRAE 62.1 outside air requirements are. But a good, estimate is about 30% outside air and 70% return air. So this air is going to come in together and it's going to get mixed. We're going to assume this exhaust is off, so we're going to have 70% return air, or it's 30% open. So we're going to have 70% return air, 30% outside air, then exhaust back out here also. So then you're going to run it through the fan. There's going to be a cooling coil that it's going to run into first, especially for cooling. If let's say you're mixing this air together, you may have 85-degree air entering this coil. So this coil is going to cool that down to the 55-degree air. This heating coil can be there for heating, or it could be there for reheat purposes also. So if you have reheat and you want to really draw that air out, this 80-degree air, let's say 70% humidity, is going to come across this coil, and this cooling coil may try to cool that air down even farther than your typical 55 in order to really dry out that air. So you're going to bring down for you to be able to use that sensible heat to increase that to 55 degrees to really reduce that humidity of the air. So that supply air is going to come and it's going to cool and condition that space as necessary. Obviously, whenever you're heating, the cooling coil is going to be off and you're just going to use that heating. You're going to do the same thing. This exhaust is important because you don't overpressurize the space. Some spaces may have other exhaust fans, and you may have air openings that the air can go above the wall, under doors, or something like that, and it'll still almost neutralize the space if you have enough exhaust fans throughout, such as in restrooms, storage areas, something like that. But sometimes those exhaust fans, there's not enough air allowing it to leave the building to prevent a very air pressurization in the building. So if you have a lot of air pressure in the building, it's overpressurized, you may have problems such as the doors may not shut. Open the door and try to shut it, slowly opens back up. Stuff like that would be, a good instance of overpressurization. So this exhaust fan really helps with that aspect. I'm going to move over to air handling units. These do the same functions as the rooftop is, except these are generally installed inside a building. And these typically do not have a compressor inside of them because, the compressor is going to build up some heat. And if it's installed inside, you're going to have a way to dissipate the heat. It's not going to build up too much because these are refrigerant cooled. But as we move forward with A2L and mildly flammable refrigerants, we're probably going to want to try to keep some of that refrigerant outside if possible. As I said, these can be variable air volume, constant air volume, DOAS units. The cooling is typically done with a chilled water. So instead of having the refrigerant come through the coil, you're going to have chilled water, which is typically going to be provided by a chiller, come through that coil to condition that air. Then hot water is typically going to be what's used for the heating side of things. You can still use gas-fired heat, but it's not as common inside. And that hot water is typically going to be provided by a boiler system. Constant air volume systems generally going to condition one large space. An example of this may be a gymnasium where you have one space that's going to need a similar load, wall that's controlling it, but it's a large space. This is typically lower cost, it's easier to control, but it may be less efficient, and it may vary because you're going to have one thermostat controlling the temperature of that space. So if you have a higher load on one side of this gymnasium, lower load on the other, it may be hotter on the high end side versus the other. Variable air volume systems typically provide cooling and heating to a number of, just a large space. A wing of a building, something like that. And a lot of times these will have a terminal box, some type of terminal box conditions. So this can help control the humidity. This can help control the actual specific temperature going into that space. There will be a hot water coil on a lot of these boxes. So for some reason, if that system needs heating, you can work with that for heating while the other side of the building needs cooling. There's a lot of options that the designer can do with these type of systems. Here's a dedicated outside air system. So this type of system is going to bring in 100% outside air to the space. These are going to be working in parallel with another type of system. So these aren't going to be the system that totally conditions the space. These are going to be working with systems such as the VRF, beam, fan coil, ventilators, something like that, which conditions the actual space. But this is simply going to bring in the outside air to the space. Here's an example. Let's say this is a school, a classroom wing. So you're going to have classrooms where we're going to bring in the blue lines are going to indicate the outside air. The yellow lines are going to indicate what the exhaust air is. So these may be storage rooms. These may be restrooms, a mechanical room where we're trying to bring in a certain amount of outside air. Then this DOAS unit will also be using this exhaust air to go through an energy recovery wheel. So this green line here indicates an energy recovery wheel on a. So you may have 75-degree exhaust air on this side of the system running through the energy recovery wheel, and you may have 90-degree outside air coming through this side of the wheel. So that wheel is going to be slowly turning, and it's going to be heating up and cooling that membrane on there. You're going to have flow across there. There will be a little bit of cross flow, but it's going to be very little, 1% type area or type percentage of that. So you may have 70-degree outside or 75-degree return air coming through here and 60% humidity, and it's going to leave at a higher temperature because of this outside air. So this outside air might be 90% or 90 degrees outside and 70% humidity. But after this heat wheel will cool this outside air down, it'll condition that air. So this out air may be 80 degrees and 65% humidity after it goes through that energy recovery wheel. This really reduces the load cooling coil for the cooling condition. So you may actually be able to undersize this cooling coil compared to what you would if you not have this heat wheel. It's also much more efficient than trying to mechanically cool that instead of using the energy recovery and just exhausting all of this air out of the building that you would be exhausting anyway and not using that energy as a reclaim. Same thing with heat in the heating mode. You're still going to be bringing back that 75-degree air back through this side of the coil, but instead of this being 90 degrees, the outside air may be 10 degrees. So you may have 10-degree air coming into the heating wheel, and on this side of the heating wheel after that, it may condition it up to 35 degrees, 40 degrees. That is a huge.
Hey, Otto.
Yes.
We did have a question come in. Can you talk about, we had one question, what is a chilled beam? Can you talk about that?
We'll be showing
one of your bullet points there, the chilled beams.
Yes, I slide on that here on a little bit farther down. I'll talk about that and show what that is.
Okay, you're also kind of cutting out every now and then. I don't know if it's your connectivity or, I mean, it's okay, but it's every now and then. Are you connected through the computer or through the phone?
Yes, I'm connected through the computer.
Okay, it's fine. You're not. We haven't completely lost you, but it's a little garbled every now and then. But you're fine. I'll let you know if it gets any worse.
Okay, sorry about that. So I guess outside air is going to do the same thing. So you're going to have, cold outside air coming in, and this heat wheel is going to do a good job of conditioning that air before it goes into through this heating coil. That can really reduce the size of that coil, and it's going to greatly increase that efficiency of the system. Another benefit of these type of systems is that you have no air recirculation. So you don't have exhaust air coming back to this DOAS unit. That all that exhaust air is going to be leaving the building. So you don't have air that's going to recirculate from this classroom over to this classroom like a VAV system. They're going to be completely separate. You're not going to have air changeover from one to the other. Here's an example of a VRF system. It's most commonly referred to as VRF. Daikin calls it VRV, but That's their patent on the name. So this is a variable refrigerant flow systems. OEMs that make these could be, you know, Daikin, Mitsubishi, LG. There's a few others that make. Um, these type systems typically can do cooling and heating at the same time. So let's say you have a bunch of outside walls in the winter that need heating. Well, your indoor may need cooling at that time because you don't have a heat load from the outside. All your heat loads internal to the space, you know, a very efficient system, especially if you have spaces that need cooling and other spaces that need heating at the same time. This unit's going to work the same hard as if it needs to cool 5 spaces as it would if it needs to cool 5 spaces and heat 5 spaces. I'm going to show an example right here. You can see my mouse. Right here is an example of a VRF indoor unit. This would be mounted in the ceiling above. So you're going to that unit itself. And these black lines are actually refrigerant lines running throughout the space above. So you're going to have your outdoor unit, which is the one on the left here, shown here, and it's going to run refrigerant to a box. And this box is what's going to control if you have hot refrigerant going out or if you have cold refrigerant going out to the individual spaces. Allows you to do simultaneous heating and cooling at the same time with a VRF system. Some of the advantages are you're going to have smaller piping, less. The ductwork you're going to have is going to be simply the dedicated outdoor air system ductwork, which, you know, may be 1/3 of the size of what you would traditionally do if you have a VAV system, because you're bringing in 1/3 of the air. So that may help if you have retrofits, if you have very small spaces above the ceiling to be able to run the ductwork or water pipe, something like that. These are very good systems for retrofits. Some of the disadvantages are you have refrigerant running above the space. As we move to mildly flammable refrigerants, that could be a big concern for a lot of these systems. A lot of the buildings and probably building codes aren't going to like having highly flammable refrigerant running above the space. I'm not aware of what that answer would be at this point. That's something that the VRF industry is working hard on to try to improve and, you know, mitigate the risk of not being able to sell these units where mildly flammable refrigerants are needed. An example of a chilled beam that was asked earlier. The one on the right here, mounted ceiling. So chilled beams are going to have through. So these units to move the air. So you're going to have your outside air, and the difference in temperature in that beam is going to allow you to move air, more air than what's just brought in through this outside air. So let's say we have this 1:3 ventilation to induced air ratio. So that means if you bring in 100 CFM of outside air into that space, you can actually supply 300 CFM of air out of this beam through induction. The outside sides of this beam is the supply air, and the inside is what would be the return air directly from this space. So this is another example of you don't have any air crossing over from one space to another. So one classroom is not going to be receiving the same air that the other classroom just returned back to the system. This is another good thing about the system is there's no fans, so it's quiet. You're not going to have the fan running above, kind of like you do at VRF systems. You're going to have a fan in that space moving the air, or a unit ventilator, or a fan coil installed directly above the system. These are good units to in sound sensitive rooms. It's also efficient as well. Yeah, this would use a chilled water loop to cool and a hot water loop to heat. So some of these systems going to have a hot water coil and a chilled water coil. Some will just have one coil, and there will be a valve that will open and shut to say if that needs to be hot or cold water. It really depends on the system design and the chill beam design, and it's going to affect the price of the system as well. The these systems, since they're running chilled water above the space, you're going to have to do proper insulation to avoid condensation above the space, so you don't start getting water dripping on your ceiling and causing a mess. One benefit is, chilled water piping is typically smaller than what duct work is. So this is another good option for retrofits. If you have a little bit of space above the ceiling, it's not a new design that you can work with the architect to properly get enough space what you need. This is a good alternative for that. Here's an example of a fan coil unit and unit ventilators. These are, cheaper units. They will have a fan in these units. So this fan coil unit may be directly above the ceiling, or maybe a ceiling in an adjacent space. We got to be careful on where we install some of these units, because it can be louder if it's installed right above an office, something like that. It can be annoying, especially if there's a compressor in there, or if it's a digital compressor. You would not want to install a digital compressor in one of these units. That's going to change the sound up and down as it loads. So the sound is a big disadvantage of these type of units, but they have their advantages. Is if you want to do something cheap and quick, these can help quite a bit. I think Tony asked a question about how these are different from VRF systems. The VRF systems not going to have these ducted. They are going to, inside units right here, but instead of having hot or chilled water come to these spaces, they're going to have refrigerant come into these terminal units, and the VRF system can do simultaneous heating and cooling as well, which makes it more efficient than what at the same time, which is part of the reason why they're less efficient than what a VRF system is. I think we're going to try to move to hydronic systems, so water systems, systems that move chilled water, or systems that move hot water. Here's an example of a air-cooled chiller, just a picture of a Johnson Controls unit. These can be used to supply chilled water and sometimes even hot water if it's a heat recovery chiller to various units, such as a variable air volume air handling unit, constant air volume air handling unit, dedicated outside air unit, chill beams, unit ventilators, fan coils, rooftop units. Most things that you use a compressor for in a compressorized air unit, you could get your cooling out of a chiller instead of a direct expansion unit compressors on the specific unit. So we're going to have our compressors here that is going to be chilling the water instead of compressors that are going to be providing refrigerant inside the coil on a unit to condition the air. Typically, there's air-cooled chillers and there's water-cooled chillers. Most chillers that we see in the industry for comfort cooling are going to be air-cooled. So you're actually going to have air coming across the condenser to cool down the refrigerant for air-cooled. Water-cooled systems are going to typically have some type of a cooling tower or some type of device that's using water to cool down that condensing refrigerant on that side of the unit. These can be paired with geothermal, so it can be ground loops, or if you have a big lake or something like that, you can have these running out to have a cooling tower attached to them. And one of the issues with the cooling tower is that you have to make sure that you properly condition that water. So you have to treat that water, make sure that water doesn't get dirty. Then also you have the potential for quite a bit of water evaporating. This may not be an issue for some spaces, for some areas that have low water bills, or easy access to water. But if you're in a part of the country where water is expensive, these water-cooled chillers could actually be mitigated or neglected due to the water costs that you're going to have to provide to that cooling tower to overcome that evaporation loss, which is one of the benefits of the air-cooled chiller, and why air-cooled chillers are generally going to be cheaper than what your water-cooled chiller application will be. So that's one main reason why most people decide to use a air-cooled chiller instead of a water-cooled chiller. Here's a kind of an overall high-level view of a chilled water system. So you're going to have your chiller, which is going to cool down that water. So typically you're going to have a 42-degree supply water temperature going out to the space. So you're going to have a pump that's going to be moving the water throughout this entire building. And this water can go to an air handler, a unit ventilator, chilled beams, multiple air handlers, multiple ventilators, dedicated outside air systems, pretty much anything that needs to condition for cooling. So a typical air handler is going to have 42 degree that needs comfort cooling for the space. It's going to have 42-degree inlet water, and it's going to have 56-degree outlet water. One of the benefits for these systems is that, let's say, not all the spaces need as much cooling. Let's say you only need 50% cooling. Instead of having this 56-degree return water, that return water may only be 50 degrees then, which is going to make less load on this chiller. So instead of bringing this 56-degree water back and making this chiller work enough to cool 14 degrees of water, if that's 50 degrees, that chiller is only going to have to work to cool 8 degrees of water. So this type of system, um, chilled water systems does a very good job at handling various loads throughout the building and throughout each space. These air handling units a lot of times they'll have a valve which varies how much water goes through the system itself. So you don't need to have 100% water that was designed to go to this chilled water system. You may be able to reduce that down to 50%, 30%, whatever that air handler unit can withstand, enough to still provide that 55-degree cooled air to the space. Chillers can all be used as well. Typically you see boilers that's going to make up the hot water, but as we move forward, try to do more stuff with electrification instead of having natural gas on site. I think we're going to see quite a bit more heat recovery chillers that's going to be making hot water with electric. This is one of the earlier slides we showed a heat pump, the heat pump refrigeration cycle. That's exactly what this is doing. There's the hot water is going to go across the coil and it's going to heat water. So you may have 80-degree return water, and this is, well, we'll probably be higher than that. You have 100-degree return water, and this heat recovery chillers they can heat it up to 120 degrees, let's say, to condition the air for this, or to condition the water that will eventually condition. Here's just a couple examples of boilers. This is an old steam-fired boiler. But, typically, we don't see too much steam anymore. Comfort cooling. Most that we're going to see for new buildings is condensing boilers. There's going to be some non-condensing boilers as well. Really, the big difference is that the condensing boilers, you're going to want to limit that hot water supply temperature to 140-ish degrees. Non-condensing boilers, a lot of times they can get up to 180 degrees. But these condensing boilers are going to be much more efficient than what the non-condensing ones. Some of these would be 92% efficient, in that ballpark range. A lot of the non-condensing ones going to be 82% range. So the benefit of having condensing boilers versus non-condensing due to that increase in efficiency, but you have a lower supply water temperature. So a lot of that's going to require more flow of water, which is going to require larger piping throughout the building also. So your total application cost may be a little bit higher with a condensing boiler than it would be with a typical non-condensing, less efficient boiler itself. But one of the benefits for heat recovery chillers is it can do replacing these type of condensing boilers, because a lot of times you can still make 120, 130 degree hot water with a heat recovery chiller. You will struggle to make the 180 to 160 degree hot water that a non-condensing boiler would make. So that's some things to think about, in the future if people would want to retrofit systems from, natural gas fired boilers to electrification heat recovery chillers. There's going to be some limits on what that hot water temperature is. I'll come back to this another way. We don't really see electric, straight electric resistant boilers. Typically, we can see a heat recovery chiller be about 3 times more efficient than what a standard, just electric resistance, 100% electric resistance heat would be. That's why you don't see too many simple electric boilers making hot water. That'd be very inefficient and very expensive also. Again, more of a couple slides of overview. High level, what is internally to Emerson, we call a lot of things unitary, and I think a lot of people don't really understand what unitary actually is. The ASHRAE definition of unitary is it combines heating, cooling, and fan sections. Assemblies are for simplified application installations. Most things you work on for comfort cooling is going to be unitary. Some exceptions are chillers and room air conditioners. Almost everything else is going to be a unitary system. Another thing that people may see quite a bit is our operating envelope. This simplified operating envelope for the compressor itself. So we're going to have an evaporator on the bottom, then vertically we're going to have a condensing temperature. So the hotter it is outside, the higher your condensing temperature is going to be for standard cooling. The lower the supplied air temperature you're gonna want, typically is going to be your lower evaporator temperature. It's going to change for heating. Heating, it's going to be colder it is outside, it's going to be your lower evaporator temperature. And depending on what your condensing temperature is going to be decide what your supply air temperature is to the space. So as you can see in the envelope, as you get colder and colder for heating, you're going to be limited on what that condensing temperature can be in order to make that hot water or hot air. So if it's 0 degrees outside, you're not going to be able to make 40-degree hot water on most systems. There's things such as vapor injection or some of our variable speed, which allows you to operate compression ratio conditions. So those are things that OEMs are going to have to think about whenever they design systems that can heat at low ambient conditions. Show it. This operating envelope has a compression ratio. So this is high compression ratio of the envelope. It's going to be roughly a 6 value. As you can see, is the higher the compression ratio, the less efficient that compressor is going to be. The lower the compression ratio, the more efficient that compressor itself is going to be. This is important to note because how the OEM size their coil is going to affect what that compression ratio is. So let's say you have a coil that simply just wants to do the job and cool the space and is not as worried about cooling. So in order to get that 55-degree supply air temperature, that cooling coil for that rooftop unit may have a 42-degree evaporator temperature. Say the OEM says, hey, I want to be as efficient as I can. So when this 42-degree farther left, higher compression ratio, they're going to use a higher evaporator coil and use 49-degree water or refrigerant to supply that same 55-degree supply air to the space. There's give and takes. Once you get to such a large coil, you're not going to move as far right, so lower compression ratios as you would. There's a limit to what you get as a benefit to the coil size. Same thing with condenser. The larger condenser is going to allow for you to really bring that condensing temperature down. A smaller condenser is going to have that condensing temperature higher as well. And as we know, the lower the compression ratio, the more efficient the system is. That's why larger evaporator and larger condensing coils can help with the overall system efficiency. This is the last slide. It's just showing a photo of the various competitors to what the Copeland compressors are, from scrolls to rotary screw to oilless centrifugal compressors. I'm gonna see if we have any questions. I don't know if.
Yeah, I haven't seen any questions come in. Let's see, I think you've covered most of them that have been presented or that have come through the chat. Were there any other questions that came up from anyone? I don't think so. Well, thank you, Otto. I appreciate this. I think it was a good overview. We always like getting, most of these trainings have been fairly refrigeration focused, but it's always nice to bring in, you know, the air conditioning, specifically commercial air conditioning side of the business. You know, for those of you that are on the call, if you have any other topics from the air conditioning side of the business that you would like training on, or any more in-depth training on any of the stuff that Otto talked about, feel free to shoot me an email, and happy to cover that in a future session. We will go ahead and conclude now, and we'll start back up here at 12:30 with our daily update. So thank you, Otto. Appreciate the time, and thanks everybody for dialing in.
Thanks, everyone.